Hello everybody, welcome to the fourth module of our CCNA training. In the first presentation for this module, we're going to be just talking a little bit about Internet Protocol, the header, and some associated helper protocols. So as you can probably tell, we're going to be moving away from switching and onto IP and layer 3 mechanisms. So this is the IP header, and as you can tell, there's a lot of different information in this header. Just for those of us who may be unfamiliar with reading header diagrams, the header would start in the upper left corner with the version, IHL, type of service, and so forth, and it wraps around on every line. And every line in this case is represented as 32 bits of data, so 8 bytes. And then you can see it wraps around from total length down to identification on the second line, and it'll just keep wrapping around, and it ends with the data there at the end on the lower right. So as you can tell, this is the IP header. There are only a few fields in this that will be important to you, but I encourage you to review the IP header and the different fields and find out what they do and why they need to exist with respect to Internet Protocol. So the important fields that we're worried about for the IP header in this case are going to be the time to live, and typically a packet is given a specific time to live and is typically decremented as a packet goes throughout the network. And the idea behind a time to live is that we don't want a packet to circulate endlessly. IP provides sort of a time limit upon which a frame is based. And so initially this started out as the time to live was in seconds. And back when routers were still being developed, it may take more than 1 second for a router to process a packet and switch it from, basically not switch it, but to route it from one network to another. And so typically in modern networks you don't see it taking longer than 1 second, and so what will happen is this time to live field will be decremented by 1 every single time. The protocol, this describes what's in the IP packet, and so the protocol field will refer to basically what sort of either next level encapsulation or what sort of information is enclosed in the data portion. So in this case TCP or UDP may be specified, and basically it's a way for routers who receive these datagrams to inspect with a little bit less work. We also look at the source and destination address in the IP header, obviously very, very important since IP addressing is kind of what we'll be doing in the CCNA, and it's a uniquely identifiable logical address that's 32 bits long. Now it may not be unique, it is unique in a network sense, not necessarily in a global sense, and we'll actually explain a little bit more of that as we talk about NAT. And that's really pretty much it for the actual Internet Protocol so far as we need to know about it for now. Basically, all that you need to know is that it's a logical structural protocol, and we'll discuss some of the different ways that we can break down an IP address to make things make sense. And so now we're going to start talking about the helper protocols. The first one that we're going to mention is ARP, and ARP solves the problem of mapping a MAC address, a physical address, into a logical address, because MAC addresses are excessively hard to remember. If we could remember all of the MAC addresses in the world, then we wouldn't actually need IP addressing. But the whole point of IP addressing is to provide a more logical address that humans can use to map these devices into networks. And so that's what basically ARP is responsible for, taking an IP address that is known and converting it from an unknown MAC address into a known MAC address. And so here's how that works. Basically, first the device checks to see if the IP address is already in its ARP table. Its ARP table stores mappings from IP address to MAC address. If it's already in the ARP table, then it can just be processed and sent out as a frame with that MAC address. If the IP address is not in its ARP table, it will actually send an ARP request on the LAN and say, hey, who has this IP address? Tell me. And what will happen is the relevant host will respond directly to that host. Now the ARP request is sent as a broadcast to all hosts, but the ARP reply is actually only sent as a unicast to the particular host that sent the ARP request in the first place. And so because it receives a frame from the relevant host, then we would assume that that frame actually has the correct MAC address information as well. And so the mapping is created, and then the packets processed, turned into a frame, and sent out. Another thing that you guys probably use every day is domain name system. Despite the uncanny logicality of Internet Protocol, it actually makes even more sense to, rather than using numbers, actually using a naming system. For example, you don't type an IP address, you usually just type google.com if you wanted to get to google.com's search servers, for example. And so with DNS, we don't have to remember IP addresses. We can actually just use these domain names to refer to various hosts. And hosts usually will use a DNS server, and they will send a request to the DNS server saying what IP address is this name associated with, and that server will reply with a resolution, DNS resolution that resolves the name to an IP address, and then the host can process traffic normally from there. On iOS, we can actually configure name servers using the IP name server command, and as you can see, we can actually, if we want to, list more than one possible name server. Now, if no command is specified, what will happen, the iOS will actually send a DNS broadcast. It will try to find a DNS server at all interfaces on all networks, and it will try to resolve commands. And this is actually kind of annoying, and here's why. If you mistype a command, let's say you mistype config-t as confeg-t with an E, what will happen is it will think that you're trying to specify a DNS host, and it will make an effort to resolve that host, and it usually takes about 30 seconds for that resolution to time out. And when you're trying to enter a number of commands and go along speedily, it will actually cause a lot of slowdown for you. And what you can do to prevent this, you can issue the no IP name server command. This is nice if you don't have to resolve DNS names on your system. If you don't have to resolve DNS names, you type no IP name server, it won't even try to resolve mistyped commands or anything like that. It will just immediately reply and say that the host name is invalid, and then you can go about on your merry way typing the correct command. Dynamic Host Configuration Protocol is more commonly called DHCP, and you've probably heard of it before, and you've most definitely used it before, especially if you've ever connected to the Wichita State Network. Basically, DHCP allows host settings to be easily obtained on a network, and then this could be any number of settings. Most commonly, it could be IP addresses, but first we'll describe how this works. Basically, the process for DHCP is as follows. The host creates an IP broadcast and basically says, hey, if there are any DHCP servers out there, hey, send me information, send me requests. And so what will happen is all of the DHCP servers on the network will reply with their offers, and the CERT client will select one of those servers, usually based on just the first one it receives, and then will request additional information. For example, a client may need an IP address or a default gateway, or possibly information about how to reach a DNS server. And so all of that information can be conveyed from the DHCP server using this DHCP. So and the server will acknowledge that and send the information down. DHCP servers are usually used to assign a multitude of information, and actually there is a large number of things that you can do with DHCP. I'd encourage you to look into DHCP options if you're curious about all of just the wide variety that you can do with DHCP. ICMP is actually one of the most useful protocols when it comes to troubleshooting Layer 3 problems. And so ICMP basically allows hosts to communicate detailed information about the underlying network. So in other words, you can see some of the following messages. For example, echo request and echo reply, which you normally do with the command called ping. If a destination network is unreachable by a router or a destination host, the router can actually respond and say, hey, I can't get to that network, or hey, I can't get to that host. A redirect might be possible. For example, if a host has moved IP addresses, it's possible for a router to send an ICMP redirect, or for another host to send an ICMP redirect for a particular service, for example. Another one you may be familiar with is traceroute. It's used to determine a path through the network. Another one might be an alternate host address. So say, for example, a service cannot be reached at one address, it may provide another address, and these can be direct responses. Most commonly, the commands that you'll use are ping and traceroute, but there are a number of other ICMP messages that are conveyed. And that pretty much wraps it up for this first presentation. I just wanted to introduce IP sort of in a nutshell, and then get to sort of the IP addressing scheme and how it works in the next presentation. So again, leave comments. Please feel free to ask me questions in person, and I'll see you in the next video.